coming down to the chemistry department in week 6. This week we are extremely honored to have with us Dr. Lyn Evans. Dr. Lyn Evans is based at the European Council for Nuclear Research and was previously the project lead of the Large Hadron Collider. Joining CERN in 1969, Dr. Evans was responsible for conversion of the superproton synchrotron into a proton-antiproton accelerator, the first ring accelerator of this type worldwide. Dr. Evans became leader of the SPS in 1989 and later head of development for the Large Electron Positron Accelerator. In 1993, Dr. Evans was appointed project manager for the construction of the Large Hadron Collider, which oversaw the development of until 2018. In 2012, he was appointed as director of the Linear Collider collaboration to plan the next big collider after the Large Hadron Collider.
The LHC is currently the world's largest and most powerful particle accelerator, designed to address some of the most profound questions facing us today, including the origin of mass and the subtle asymmetry between matter and antimatter that is responsible for our very existence. Dr. Evans will seek to discuss these questions before describing the unique features of the design of the LHC that has opened up a new energy regime culminating in the first major discovery, the Higgs boson. To find out more about how the frontiers of engineering are combined with cutting-edge research in particle physics, may we please put our hands together to welcome Dr. Lyn Evans.
Thank you. Well, the first thing you may notice is that I've changed the title a little bit. Instead of talking about the marvel of technology, I think I want to tell you not how it was built. I will tell you how it was built, but first why it is built, and the fundamental questions that it is meant to address. So I think here you see a picture of the plain of Geneva, the airport runway. That's 4 kilometers long to give you a scale. The city of Geneva is very close to the city. Unfortunately, you can't see the Mont Blanc, which is out of the picture. And you see the trace. Of course, you can see nothing from the air. It's all underground, but you can see the trace of the Large Hadron Collider. The superproton synchrotron is here, which was the first big accelerator that I worked on in the 70s. And the Large Hadron Collider, which is 27 kilometers in circumference, and crossing the border between Switzerland and France. The border between Switzerland and France is somewhere around here. So, just a word about CERN. CERN was founded in 1954, only 9 years after the end of the war, and it was founded to bring scientific Europe back together, provide a facility that no single country could afford. And it started off with 12 member states. Now there are 23 member states, most of the Western European countries, and Israel as a member. We also have observers to council India, Japan, Russia, which is a big problem at the moment. For the moment, we are trying to keep a collaboration going with Russian scientists, but I don't think we can do it for much longer if things don't change. Turkey, the United States of America, European Commission, and UNESCO. So it is really serving a very international community. Okay, what do we do at CERN? What's the purpose? I think you know this equation. The equivalence of mass and energy, and in nuclear energy, the nuclear power station, for instance, you convert a small amount of mass into energy. We go the other way. We convert energy into mass. So that we can create the heavy objects that were present at the beginning of the universe Big Bang and are essential for our existence. So if you want to create a large mass, you need a large amount of energy, and the Higgs boson is an example of that. Now, this is a chemistry department here, so you live in a different world than me as far as energy is concerned. When we speak of mass, we don't use grams or kilograms. We use electron volts, millions electron volts, giga-electron volts for the very heavy objects. 1 electron volt is a tiny mass, 1.8 × 10 to the minus 36 kilograms. This is the energy that an electron gets when it's accelerated through 1 volt. If you wanted to give it that energy by heating it, then you would need 11,600 degrees centigrade. It wouldn't be a very efficient way of accelerating it. You can see the world that we live in today. 1 electron volt is 11,600 degrees centigrade. You cook a piece of meat in the oven at 200 degrees centigrade. Breaking of the molecular bonds are at the level of millivolts. Chemistry at the level of millivolts, volts. Even the ionizing the hydrogen atom, what's the ionization there? 13 volts, something like that, which is 6,000 degrees. So, but we are interested in teravolt energy, of order 10 to the 16 degrees. And where did 10 to the 16 degrees ever exist? And of course, it existed at the beginning of the Big Bang. And this is a cartoon that you see very often of the expansion and cooling of our universe, all the way from this singularity that was the Big Bang 13.8 billion years ago until today. And you see the time, and you see the cooling here, where today the temperature of our universe, of outer space, is 2.7 degrees Kelvin, which if you don't know the Kelvin scale, 0 Kelvin is minus 273 degrees centigrade, so it's about minus 270 centigrade in deep space, not in this room. So now we have a picture going back from the Big Bang, and we can, if we go from the Big Bang, of course there was nothing but the formation of particles of very high mass, because there was a lot of energy available, and as it cooled, then we got the quarks and the gluons. I will explain a little bit quarks and the gluons, which when it got cooler still, condensed into hydrogen ions, and there were electrons there, and there were lots and lots of photons there. And as one cools further, at about 480,000 years after the Big Bang, then it was a plasma at the time. It was completely ionized, and when you have an ionized plasma, there's photons in there, and the photons scatter in the charged field. And so they're trapped; they can't get out. But as soon as it cooled enough for an electron to combine with a proton to form hydrogen, which is neutral, then the plasma disappeared and the light was liberated. And that light is still with us today. It's called the cosmic microwave background, and I will say a word about that. The LHC, and then of course, then you started to have the luminous objects, star formation, etc. And that's about 1 billion years after the Big Bang. So with our telescopes, we can look back about 12.5 billion years. With the cosmic microwave background, we can look back much further, within 500,000 years after the Big Bang. And with the LHC, we could look around 10 to the minus 10 of a second after the Big Bang. Unfortunately, we can't look before Big Bang. We don't know what happened then. And over the years, we have tried to recreate these conditions in our accelerators, and we have discovered, and there, since I'm in the chemistry department, you know the Mendeleev table of the periodic table of the elements, where you start with hydrogen, and then you build up in complexity in the atoms. We go the other way. We start with hydrogen, and then we try to simplify and see what the fundamental particles and forces of nature are. And out of that, we have got a very simple picture. It's not really simple, but of the standard model of particle physics, what we are fundamentally made of. And this is it. It's missing two things, but no, our universe today is like that. We need the rest. So we know now that we are made out of matter particles called fermions. These particles are the up and the down quark, the neutrino and the electron. The electron has been around for J.J. Thomson, beginning of the 20th century, of course. The neutrinos more recent, and the up and down quarks, we started to see the quark structure in about 1966. There are two more generations of exactly the same thing. Heavier versions of the same family. The up-down neutrino electron, we found that they exist in charm quark, strange quark, muon neutrino, the muon, the heavy electron, and the top quark, the bottom quark, the tau neutrino, and the tau electron. And all of these have a mass, and they have a charge, and they have a spin. And then we have the force particles, which are bosons, which are spin 1 particles. And these are the force particles, the photon, which is responsible for electromagnetism, the muon, responsible for the strong interaction, and the two particles that we discovered in the SPS collider that we mentioned in the early 80s, the W and Z, responsible for the weak interaction. So how does all this work? To make our matter today, if you want to make, and you notice that the charge of the quarks is not integer. 2/3, 1/3, or minus 1/3. So to make a proton, a proton consists of 2 up quarks and a down quark. Let's see, 2 up quarks is 2/3, plus 2/3 is 4/3, minus 1/3 is 1, so it's got a charge of plus 1. And the strong forces, gluons, are holding the quarks together inside the proton. If you want to make a hydrogen atom, then you have an electron, which uses the photon as the part of holding it into a stable state, and you've got the proton. The other particle that exists in our world today is the neutron. The neutron contains an up and 2 down quarks. An up is 2/3, 2 down quarks is minus 2/3, so it's neutral, as we know. And again, the proton and neutron are very similar, except one is good charge and one is not, and one is slightly heavier than the other. The other 2 families, we don't really know why they're there. We know they exist because we can make them in our accelerators. But to really, on a fundamental level, understanding what they are there for, it's not obvious. So let's start now by the first real problem that we have built the LHC to really resolve, is the origin of mass. you see you've got a mass here of the up quark 2.4 MeV, million electron volts. You've got the down quark, which is 1.2 GeV, which is 500 times heavier. And then you've got the top quark of 171.2 GeV. And same thing all the way down. You've got these masses that are increasing. And why? I mean, what determines the mass of particles? You've got the photon, which has got no mass, and the gluon, which has got zero mass. Doesn't mean the photon is useless. Your mobile phones wouldn't work out. But these particles have no mass. And this is where the Higgs comes in. In the early 60s, there were theorists working on a theory called electroweak symmetry breaking, which predicted that there should be a field which is in all of space, and these particles couple to that field. Now, it's saying coupling. What does it mean, coupling to the field? I mean, it's very difficult to make any simple analogy. One really not very good analogy is the difference between mass and weight. You have mass, but you have weight, so you're coupling to the gravitational field. On Earth, you have weight. You go up into space, and you're weightless. You're not massless, but you're weightless. Because you couple very little to the gravitational field. And the Higgs field should, these coupling, the photon should not couple at all, should have zero mass and travel at the speed of light. Whereas the top quark is like going through treacle. It's really strongly coupled to the field, and therefore it's very heavy, etc. Now, this field, this strange field, it's all right to postulate it, but how do you prove it's there? And this is where Peter Higgs made the breakthrough. There were several theorists who were working on this problem and come to the same conclusion that it had to be this field. But Peter Higgs realized that if the field existed, like any other quantum system, there should be a quantum of the field. The electromagnetic field has got the photon as a quantum. So he said that if the field existed, it should have a particle associated with it, and it should be possible to excite the field to manifest the presence of that particle. And therefore it was called the Higgs boson, and that's why Peter Higgs got the Nobel Prize rather than other people. The realization that there should be a particle associated with the field. So that was the first, we've been looking for the Higgs boson for many years, but there is no theoretical guidance as to the mass of the Higgs. So we've been building these particle accelerators with not a clue of whether they produce enough energy to actually make the Higgs boson. If it's too low, they can never make it. So this was the first thing the first important question is this the origin of mass or not? And that's one of the reasons that we built the LHC. We built it so that if the Higgs boson existed, we had no idea of the range of mass, but we did have an idea of maximum possible upper limit of mass. So we built it that we would cover all the way up to the upper limit of 5 TeV approximately, so that if the Higgs boson existed, we would find it. It would not be easy to find, and it was not easy to find. But as you know now, so the Higgs boson is another kind of particle. It's got a mass of 125 GeV, and it endows all the other particles with mass. There is one force that is not on this thing as wheel. It's been known forever, and that's the force of gravity. Gravity is more than 20 orders of magnitude weaker than these forces, and up to now, there's been, and I mean the holy grail there is to have a theory of quantum gravity, that we can integrate gravity into this picture, and it's not succeeded up to now. Gravity is the longest known and the least understood of our forces, actually. But this together with the Higgs, I think completes the standard model, except that we also discovered antimatter. So this picture here has got exactly the same picture where all the charges of particles are reversed, and it's a world of antimatter. We can make antimatter in our, so problem number one, origin of mass, the Higgs boson. Problem number two is now going to be the thing called CP violation, which is this asymmetry between matter and antimatter. We can make antimatter in our accelerators, and we do. I don't know if any of you ever read this book, Angels and Demons. It's a book by Dan Brown, which was a complete flop actually when it came out. We picked it up at CERN because it was about CERN. It was about people stealing antimatter from CERN to blow up the Vatican using antimatter bottles. It was total flop. And then Dan Brown, 2 years later, he wrote the Da Vinci Code, which is a terrific big seller. And suddenly, I see on the bookshelf, his new bestseller. They bring this out as being his new book, and there was a film, and it was a great success afterwards. So antimatter, we make it, but it's not that easy for people to come and steal it. It's made in this machine here, which is the antiproton accumulator, where we the antimatter we make by bombarding a material target with protons from one of our smaller accelerators. We need about 10 GeV minimum. We use 26 GeV to make antiprotons, and we accumulate them over many hours and store them in this ring. And that's the antiproton accumulator, and it was used for the antiproton collider, which discovered the W and Z boson, which I won't talk about, but it's still being used now to do experiments on antimatter, because we can capture the antiprotons in a magnetic trap. This is a small magnetic trap, and we can also introduce anti-electron and make anti-hydrogen. That's what that research is going on at CERN now, and we can do spectroscopy on anti-hydrogen. Compare the spectroscopy, and we can even do, very recently, a result has come out where the result probably should have been obvious, is the effect on gravity on antimatter. Does it go up or down? What was found is absolutely identical. So going on into the story of antimatter and CP violation, this is a little. You see, antimatter was the anti-electron was postulated by Dirac in about 1925, I think, here in Cambridge. It was in the 1930s that the first anti-electron, the positron, was discovered in cosmic rays. And it's only now that it's really becoming a useful tool for science and for medicine, and I'm going to show you why. So this year is a real event where there is an evacuated pipe here, where an anti-electron is introduced. Of course, the gas is not perfect, so at some point the anti-electron will interact with the gas atom or molecule, the electron in it, and when matter and antimatter interact, they annihilate each other. They don't like each other. And what you see here is electron-positron annihilation. Forget about the yellow stuff. That's a nuclear disintegration. But this red line I want to explain to you because it's the fundamental basis even for the LHC today. So what we have is this is a very, very simple operator. And when you see an LHC detector, you recognize parts of it. So a chamber here, and around it there are blocks of crystal of cesium iodide. Cesium iodide has got a special property when gamma rays hit it, it scintillates, it gives it off light. And this is annihilation between an electron and a positron. And that annihilation is going to obey the law of physics, two important laws of physics. The law of conservation of momentum and energy. Now, the law of conservation of momentum says that if there was no momentum in the system at the start, there can be no at the end, then at the end. So the only way, and when they annihilate, they give up two photons, and the only way they can give the two photons off is to go back to back, directly back to back, because they have to conserve momentum. So, what you see here, and then the law of conservation of energy will tell you what the energy of these photons is. The two electrons are 517 keV, and therefore the photons of that energy, which are gamma rays. And so you can see this annihilation here, where there are two gamma rays shooting off back to back, and recording simultaneously, more or less, depending on where they are along this line, in two scintillator elements, and producing a straight line. So that's quite interesting, but where is it useful today? Now, suppose that you had a blob of antimatter instead of just a single annihilation. Then there would be annihilations going on at all angles. So there will be these lines drawn at all angles, and you would know the location of that blob. And that's exactly now what is being done in positron emission tomography. This is a very modern technique using antimatter. In fact, what happens here is that a patient is injected with a sugar which has been made beta radioactive by radiation in a small cyclotron, and it's a beta emitter, which means it emits positrons. And that sugar is injected into a patient, and it accumulates in regions of high metabolic activity. And these machines, normally they have combined positron PET scan. So you see the crystals here, just like before, and you see all the annihilations, and a CT scan, which is a very precise X-ray. So between the two, the CT scan sees tumorosity, and the PET scan sees high concentrations of high metabolic activity. And this is used to look for metastatic cancer, for instance, and many other things. So antimatter is really useful, but it took us 70 or 80 years to know why. Okay, now let's go back to the Big Bang and in our accelerators, when we create antimatter, we create precisely the same amount of matter. So if we create an antiproton, we must create another proton. If in the Big Bang that had been absolutely identical, then we would have light, and that light is with us today. It's called the cosmic microwave background, and it's fantastic. This is fantastic science, actually. This is the measurement of the temperature of the cosmic microwave background through our universe. The temperature is 2.7 Kelvin, as I told you, the temperature of deep space now. These photons, they were gamma rays originally, but the universe is stretched, and the wavelength is stretched so much they're now in the microwave region. The uniformity of temperature is incredible. 1 in 10,000. And for those of you who know what I'm saying, this is the most perfect black body radiator in nature, which means that it is in absolutely perfect thermal equilibrium. And it kind of, to be in thermal equilibrium, you have to be in contact. You know, a cup of coffee is in thermal equilibrium, but two things far apart or not. So this is overwhelming evidence of the Big Bang itself. This thermalized during the first instance of the Big Bang, and now that radiation is with us, we can measure lots of its properties. But the real point is that if there had been that perfect symmetry between the matter and antimatter, this would be our universe. There would be no place for us in it. The only reason we exist is from a subtle broken symmetry, so that there was a slight excess of matter over antimatter, and that slight excess is producing our billions of galaxies and stars. Now, hard to imagine, I know, but the scientific evidence is absolutely there. So this would have been a pretty boring universe for nobody would be living in. So I think the second objective of the LHC, and this is where Cambridge is much involved, is the understanding of I think of CP violation, which is this asymmetry. And there's a specific experiment on which Cambridge is part of the collaboration called LHCb. So that's the second thing. So we made very big progress on Higgs. We made considerable progress in better understanding of this CP violation. And the third thing, now you all know about, it was first postulated by this guy in the early 1930s. His name is Fritz Zwicky, who was a Swiss German, but he was working in Caltech. And apparently he was not a very nice character. Even I'm not old enough to have met him, but he was not a very nice character, but he was a very brilliant character. And he was studying in the 30s concentration of galaxies in certain parts of the sky. And he was telling everyone that there is not enough visible matter in these galaxies to keep them together. But nobody would listen to him. I think this just went along for a long time, until somebody much more reasonable came along. This is Vera Rubin, who actually recently died. And in the early 90s, 80s and 90s, she set up a program of measuring the rotational velocity of galaxies. This is a nice spiral galaxy here, seen face on. This is rotating. And one thing that is fairly easy to measure in astronomy, the distances are difficult, but speeds are not, using the Doppler effect, which you all presumably know. Something moving away from you is redshifted. If you take a hydrogen line, for instance, you'll find it redshifted, and it's moving towards you is blue shifted, and you can use it to measure the speed. So she measured many of these things. Of course, these galaxies have to be side on in order to do that measurement, but there are plenty that are side on. And she measured the rotational velocity as a function of radius, going far up into the dark regions of these galaxies. And what she got was a big surprise. Instead of what you would expect is the velocity to be rapidly reducing at large amplitude where there's very little matter. But what you find, and you find it universally, is it's not at all flat. So the only explanation here is that there's got to be objects, matter, which is not interacting in the normal way with other material, giving off light, etc. But it's got a gravitational effect. It's gravitational effect that holds this together. So that was another piece of evidence for the existence of dark matter. And then a third piece of evidence came from galactic lensing. When light passes through a gravitational field, it bends. And so if you observe a faraway object and there's a very strong gravitational field between it and you, then you will get a distortion of the object to the point where this is the most famous one. This is Einstein's cross, gravitational lens G2237, where that is actually a single object with a large gravitational mass in front of it, and the light is being, it should be anomalous if it's perfect. The light is being distorted by the gravitational field that you can't see. And that's been used now for many measurements of, this is the able galactic cluster, and with computers you can extract the position of the dark matter that's producing the effect. You see all these distorted galaxies. You can even see some ring-like structure due to some very strong gravitational field, which you can't see, distorting. So for dark matter, there is absolutely no doubt. Dark matter is there. There are three independent ways of measuring it, which is good, but we don't have a clue what it is. So the NHC now is working. There is a worldwide effort working on trying to find dark matter. We don't know if it's hot dark matter, very energetic, or if it's cold dark matter, very low energy. So there is a whole spectrum of experiments around the world doing dark matter experiments to try to understand this very important problem, because it is a very important problem. I'll go to the last thing. Of course, it's something that you. Oh yeah, that's a nice picture of the bullet galactic clusters coalescing, and you see the visible matter, the stuff that gives off light, and then out from the gravitational lensing you can recreate the dark matter. So the visible stuff is interacting, and the dark matter is going through each other without any effect. Finally, of course, you've heard of dark energy. Now, dark energy is nothing like as solid as the dark matter. I think in the different ways that we can see it. Dark energy, that's only a bit more than 20 years old, where astronomers started measuring at very large distance the redshift of the expansion of our galaxy, and using a thing called Type 1a supernova, which explode with a very well-defined luminosity. So if they all have the same real luminosity, then the distance away can be found by the inverse square law. Very far away is going to be much weaker. And what they've found, of course, is that what is expected is that the universe should be slowing down in its expansion as the gravitational field dilutes. What they found was the exact opposite. At very large redshift, it's speeding up again. It's like a negative gravity. So there, I think the experimental evidence is less solid. There are not many different ways of understanding it, but I think who knows what the solution of that is. It may need a modification of Einstein's general relativity. Now, when you put it all together, it's very sobering that you have, this is the energy pie for our universe. And what we understand and what we can see is 4%, 3.6% intergalactic gas, and 0.4% stars, etc. 22% of dark matter, and 74% of dark energy, if it exists. And like I say, it could be modification of the general relativity, maybe able to explain it. But at least we understand a very small amount of our universe. So that's the third thing. Dark matter, at least, I'm sure that energy can make a contribution to understanding it. Dark energy, I'm not so sure. Okay, now let's go on to talk about the energy. Tell you what, let's get on to engineering instead of science. So particle accelerator, like the LHC, I'll show you how it works. So you saw that circular ring, 27 kilometers in circumference, and that is used to put in magnets, which bend the beam round in a circular orbit. Magnets do not accelerate the beam; they can only guide it. To accelerate the beam, you've got to put somewhere around the ring an electric field, a longitudinal electric field, to give the beam a push. And that electric field is generated in radio frequency cavities. These are cavities which are excited in where there is a longitudinal electric field mode. So they're oscillating, powered by radio transmitter, effectively very high power transmitter into a cavity. And if this works, you can see it, a cartoon. Does it look? Yes, it does. So what you see here is the particle going around, and you see it is, every time it comes around, it is synchronous with the field. The field is always in the same direction. So it gets a slight increase in energy. Two consequences of that slight increase in energy is that it's got to be a slight increase in magnetic field to keep the beam in the middle, and there's going to be a change of frequency in the cavity because the beam is going to come around quicker. So there's this balance between increase. An LHC will take 20 minutes to accelerate the beam like this. You can accelerate it until the magnetic field saturates, since you can't, and then you can't get any more energy out, even though the RF cavity could get it. So at some point the field will saturate, and you can keep the beam going round and round for a very long time, hundreds of hours, but you can't get any more energy out of it. Now, until the end of the 1960s, our experiments used to be done in a way that you would have one ring, you accelerate the beam towards top energy given by the electromagnets at the time, which are about 1 Tesla from conventional electromagnets with iron, maybe 1.5, maybe a little bit higher. And then you kick it up and put it on a target where the beam would hit the target nucleons and secondary particles would be produced. And that's a very inefficient way of doing it, because of course when you hit stationary target, there's a knock-on energy, and the actual energy available for producing new particles is much less than the beam energy. And in fact, it only goes as a square root of the beam energy. So if I took the 400 GeV SPS that I mentioned, used as a fixed target machine, the energy available is 35 GeV for producing new particles. Used as a collider, the energy available is 800 GeV. So having a colliding beam device is a huge boost. So the LHC is a colliding beam device. It's not one ring, it's two rings with the beams going in opposite directions. And you see a schematic of the layout of the LHC here, where you see the two rings, 27 kilometers, and you see the beams are separate into two separate channels for most of the time. They are, and they divide up into sectors. These sectors are about 3.4 kilometers long, each of them. There are 4 places where the beams are made to be brought into collision. There is points 1 and 5, Atlas and CMS, the very big experiments in the LHC, which are general purpose detectors. Not really specialized at all, but they can see everything. The one at point 8 is called LHCb. This is the one for CP violation, for the antimatter And this is one where Cambridge has got an important group working, I think. And at point 2, there is another experiment which is a little bit special, and that is about one month a year we use the LC to accelerate not protons but lead ions, heavy ions, and that produces a thing called the quark-gluon plasma, which is the soup where there were early free quarks and gluons which then coalesced to make the protons about 1 microsecond after the Big Bang, not 10 to the minus 10 seconds. So and that operates in ion mode for a small part of the year. So that's how the LC looks. It's part of a complex because there's the whole of the CERN infrastructure built up over 50 years is there because the beam is accelerated. It starts with a bottle of hydrogen which is then ionized. The protons are accelerated in a linear accelerator, and then a various chain of accelerators. Each one of them goes up to the maximum field it can achieve, and then it passes it on to the next one. So through these machines, I think there's a little cartoon here which is, so you see the filling of the LC is not very good, but you inject the beam into the 2 rings in opposite directions, and you collide them in the various detectors. They've got to be synchronized to a fraction of a nanosecond to be actually applied in the detectors, not outside. And this is the Atlas detector where you get results of collision, which you have to analyze a thing like that. And a Higgs boson is one event in 1,000 million of these. You've got to be able to find it in 1,000 million interactions. So that's the way the complex works, using all of the accelerators of CERN, all the way from the beginning. Okay, this is a picture of the LHC. Where are the 2 rings? So this is first of all, the LHC is not a normal electromagnet. It's got to be a much higher field than that. And so it's a superconducting machine, so it's going to be cold. It's in fact very cold. So it's got to be inside a cryostat that allows it to be kept cold. And these are the LHC magnets. You can see them being bending, but not very easily. Inside that cryostat, then you see the 2 rings. So inside the cryostat, you have an iron yoke to contain the magnetic flux. You have the 2 beam pipes here and here, and around the beam pipes are the superconducting coils that produce the magnetic field, which is vertically up in one aperture and down in the other aperture, which is what you need with 2 beams going in opposite directions. And all of this is inside the cryostat, and it's 5,000 tons of material that has to be cooled to 1.9 degrees Kelvin. I told you the LHC is colder than deep space. So this is an LHC dipole. There are also focusing. Every 4 dipole there is a focusing magnet, which is much smaller, keeping the beam size under control. And this is very well isolated against the incoming heat. Now, one of the tricks of this not 2-in-1 structure. We did it like that because, first of all, the tunnel is too small to put 2 separate rings, and secondly, it's cheaper and it's clever because you see the magnetic flux lines in these magnets. The beam is going up in one direction, and magnetic flux lines have to loop around the currents always. So it loops around like this. And on this side, it loops around through here and through the other aperture. There is very little flux in the center here. If it were the opposite way and it was up and up in both apertures, then you would pile flux through this region from both apertures, be very quickly saturated, and it wouldn't work at high field. And in fact, we could get about 4 Tesla with the up configuration, and 9 Tesla with the up down. So I think that's an excuse of the LHC that people don't usually realize. Now, the LHC is a massive exercise in superconductivity. And not only superconductivity, I would tell you about superfluidity. And I will show you how helium becomes superfluid, I hope. This is the first superconductor was discovered by Camerionis in 1908. And he found superconductivity in mercury at 4.8 Kelvin. Now, mercury is not a very useful material for building coils with, but he soon found other materials where which were metallic, which were superconducting, and he got very excited that he could put a current into these coils without any electrical resistance at all. Except he very quickly learned about the critical current, where as you increase the current, at some point you will lose the superconductivity. He also discovered the critical temperature, that if you reduce the temperature further, then you can push the critical current up until it hits a brick wall. So you've got these two things, the critical current and the critical temperature. This is a piece of superconductor from the LHC. It's a flat cable. This is a picture of it from the side. I think there are 32 strands. The strands look like just ordinary copper wire from the outside. But if you etch away into the strands, what you find that each single strand has got 9,000 filaments of niobium titanium alloy. You can see it here, but you can see a micrograph here inside these filaments. And the copper is only there to stabilize it. Copper is not a superconductor. The current of 12,000 amperes is being carried by these tiny filaments. So that's the first thing, making 7,000 kilometers of this stuff by extrusion and very complicated process. The second trick is that we wanted, I told you, we wanted to produce a machine that could go to the maximum possible energy, cover all bases for the Higgs boson. And if you use a normal superconductor, even that one, and you use it in liquid helium, which is at 4.2 Kelvin, then you get a certain, what's called a load line. As the field goes up, the critical current goes down. This is the limit line, if you like. But we wanted much more than that to go to a higher field. And there were in principle two ways of doing that. There is a superconductor called niobium 3 tin, which has got a much higher critical current. This one, much higher critical current. So there could have been possibility of building a machine with niobium 3 tin and helium at 4.2 Kelvin. But niobium 3 tin is terrible stuff. It's like glass. It's very, very difficult to work with, and it would have been financially impossible anyway. But there is another way of getting to the much higher fields that we need, and that is to cool the machine down to lower temperature. And if we cool this superconductor down from 4.2 Kelvin to 1.8 Kelvin, then you get a 3 Tesla shift. So a maximum of 6 Tesla in a normal superconducting machine becomes 9 Tesla, and that's what we have in the LHC. But we have to cool it down to 1.9 Kelvin in the LHC. And there is another problem. How many of you know about superfluid helium? So I'll show you it. So helium is a strange liquid. As you cool down helium, first of all, how would you cool down helium? You liquefy it with a liquefier, but to go down further, the only realistic way is to reduce the vapor pressure. You must all know that water boils at a lower temperature on top of a high mountain than it does at sea level, because of the atmospheric pressure is lower. So if you want to reduce the temperature of the helium, you have to pump on it, and you have to produce a pretty good vacuum actually to get down to very low temperature. And when you do that, then you come, there is a temperature 2.17 Kelvin precisely, with something bizarre happens. And I will take you through that now. Again, I always cross my fingers for these things, if they work or not. Good. So what you see now is helium is boiling, it's being pumped on, the temperature starts here at 2.3. And it's going down, the pressure is reducing to 50 millibar above the liquid, then something fantastic happens. And that's the point where there is a phase transition. It's like water turning into ice. But it's a quantum mechanical phase transition. The properties obey the laws of quantum mechanics after that and lower. And there are some very bizarre properties. So first of all, why does that boiling stop? Well, why does boiling happen in the first place? It happens because there's a temperature gradient between the bottom and the top of the liquid. And the bottom is hotter and therefore bubbles come up. When it goes into that state, then the thermal conductivity suddenly becomes extremely high. And when the thermal conductivity is extremely high, then you cannot support the temperature gradient, and therefore you cannot support boiling. So this is one of the properties of superfluid helium that we need to harness as an engineering material. Don't forget, we need it in order to get a very high field. But in getting it, we're given this gift of extremely high thermal conductivity, and then a second property, which is not such a gift. Which is not such a gift, especially for the welders. Is this is a beaker which has got a bottom which is very slightly porous. It will contain liquid helium perfectly well, as you will see, but you will see what happens when it goes superfluid. It didn't work. Good. So you recognize the phase transition, and this will be fast. Bam, right? Look at the bottom of the container. The liquid is pouring out of the container, and that is because when it makes this transition, it has got zero viscosity. It will go through the tiniest capillaries, which is why I made the remark about the welders, because they have to weld things which are absolutely perfect to contain it. So extremely high thermal conductivity is an important feature. It's also got, which is probably less obvious to you, it's got a huge specific heat. So this is the specific heat of material, like the niobium titanium conductor, which is going down as 1 upon T cubed in this temperature regime. And this is the specific heat of this helium, which is many orders of magnitude higher. That's important to us because this stuff with a very, very low specific heat, any transient temperature input to it will increase the temperature a large amount. That's what specific heat is, right? The ability to absorb any heat, and the magnet will quench. So we need to build these coils of these magnets so that they are porous. That this helium permeates inside of the coils because of the fact there is no viscosity, and helps with this enormous specific heat to buffer any transients. So putting all that together, I think this is the thermal conductivity. And you see at the lambda point, 2.17 Kelvin, it shoots up. This is the very best copper, oxygen-free high conductivity copper, and the helium is huge thermal conductivity. And this is the biggest trick of them all, because I show you now a sector. I told you that the LHC is divided into 8 sectors. Each sector has got to be cooled down. It's cooled down separately with a refrigerator at the end of the sector. And in each sector, 3.3 kilometers long, there are 156 magnets in series, and they all have a thermometer in them to measure their temperature. In this sector, from 0.4 to 0.5, the refrigerator is here at 0.4, and there's nothing at 0.5. So what you would expect is to see a temperature gradient that would be cold here and warm here. And that is the case. When you are cooling the thing down, there is this temperature gradient. But as soon as you cross the lambda point, it collapses. The column of helium, 3.4 kilometers long, cannot support any temperature gradient at all. And it collapses to a point where the temperature is uniform to millikelvin. It's incredible. So I think this is the way that we use, these are the ways that we use the strange forms of superfluid helium. It's semi-conductivity for that. It's the lack of the viscosity, and it's huge. It's specific heat. It's a unique material. Okay, now I'm coming to the end. Oh, wait, can I do 5 minutes more? Yeah. Now I'll go very fast, but I'm just showing pictures. Huh? So this was a huge manufacturing process, and you see here the coils being made of the magnets, which are 14 meters long, put into the cryostats. You can recognize what I showed you before. Put on test benches to each one has to be cooled down and warmed up. These benches run for 4 years, 24 hours a day, 7 days a week, with only 2 weeks a year for maintenance. Magnets lowered into the tunnel. Transport in the tunnel. There is only one shaft that can lower that magnet, and then the transport in a very tight region. The furthest distance is 15 kilometers at 3 kilometers an hour. Not a very nice job driving the thing, but it's got assistance from that line there. Interconnects, connecting the magnets in series together, and you see the finalization. You can see one of the bead maps here. This one here, and there's another one on the other side, and these are carrying the bus bars that are going through. Now, very good now, because the detectors, just a word about the detectors. There are 4 detectors, I told you. They're underground, 100 meters underground in caverns, and they are Atlas and CMS, the 2 very, very big ones. The LECB and Cambridge is in Atlas as well. LECB and Alice. Alice is the one with the heavy ions. And these things are huge. I think CMS is 12,500 tons. More than 3,000 scientists now from more than 180 institutes. I'm sure this is old. So it is an incredible collaboration, both CMS and Atlas. This is CMS being the biggest piece being lower down into the tunnel. That's 2,000 ton piece. This is Atlas, which is actually lighter than CMS, but it's physically much bigger. It's a lot of air. And you can see a person here just to calibrate it, and there's an even better calibration somewhere. Here, you can see a real person. Here, and the beam is coming straight out of the board and colliding in the center of Atlas. So it's absolutely huge. So this is a Higgs candidate coming from CMS. This is Higgs to gamma gamma, which is just like I showed you the annihilation between the electron and the positron. The 2 photons go off back to back. Now they don't go back to back here, but in their own reference frame they are, because there is an energy difference. The quarks in the proton. We're not interested in the collision of protons. We're interested in the collision of the pips, the quarks inside the proton. And there's an energy distribution amongst those quarks. So there will be one high energy quark colliding with a lower energy quark. Therefore, the center of mass is not the same as what you see in the lab. And that's why in the true center of mass, this is sparkle back, but in the lab it's not. And of course, measuring the energies of these two gammas from the Higgs decay gives you the Higgs mass, but not just one event. And that's the same thing in CMS, where it's shown from the front, so it looks like more back to back. And then just to end, I think a fantastic seminar it's a long time ago now. We just celebrated the 10th anniversary, where the two big experiments showed the results double blind. And this is an example. This is Higgs to gamma gamma. So there's a huge background. There's loads of things that can produce gamma gamma. Massive background. What is this? Is the number of events per 5 GeV, I suppose, bin like this. Massive background, but on top of that background there is a signal, which is an enhancement because of the decay of the Higgs boson, and that signal is at 125 GeV. Atlas produced the result first, which if it had been alone, that would not be enough to announce the discovery. And then CMS, which has got a completely different technique of measuring energy, etc., produced this curve. And this blew our minds. Exactly the same. So that was the real discovery of the Higgs. Now there's much more data. That peak is huge. It was an event. We had a visit from Peter Higgs himself. This is Peter Higgs, who won the Nobel Prize a year after that, and he was quite embarrassed actually of the amount of effort that we had to make to find his particle, but he was very happy to receive the Nobel Prize. So finally, I just wanted to make a point. I think I started off by saying why CERN was founded. One of the reasons promoting peaceful collaboration, and I think that's even more important now. We have a big issue on our hands at the moment. Can we keep the present scientists with us or not? But we have to do everything we can, even if the politicians screw up. The scientific community collaborate in peace, trying to solve the most fundamental issues, and I hope some of them I've explained to you today. Okay, thank you. Sorry to keep this long. I didn't realize.